The purpose of radiography is straightforward. Send high-energy photons into the human body and measure what comes out the other side. As those photons travel through tissue, the beam's overall intensity drops. We call this reduction attenuation. This diagram maps beam intensity moving through tissue. The decay follows an exponential curve, dropping rapidly but never hitting the zero axis. Why? Look at individual photons. Some are transmitted, passing completely through unaffected or with lowered energy. Others are absorbed. These photons transfer 100% of their energy to the matter, stopping abruptly and failing to reach the film. The rest are scattered. They deflect off their original path, sometimes losing energy in the process. What you see on a clinical radiograph is exactly that, the surviving transmitted photons. It is the negative space left behind by the billions of photons that were either absorbed or scattered. To determine exactly which photons survive that journey, we have to scale down from the macroscopic block of tissue to the quantum level of individual atoms. When a photon hits an atom, it can bounce off a firmly bound electron without losing energy or causing ionization. This is elastic scatter. Because elastic scatter causes no downstream effects in the material, it has almost no diagnostic significance in radiology. We can ignore it. The true drivers of clinical attenuation are two competing processes, the photoelectric effect and Compton scatter. These two interactions dictate the final outcome of every scan, controlling everything from image contrast to patient radiation dose. Mastering the physics of radiography means understanding exactly how variables like atomic number, mass density, and photon energy determine which of these two events occurs. In this model, the photoelectric effect occurs deep within the atom. An incoming photon strikes an inner shell electron, transferring all its energy. The photoelectron ejects, leaving a hole. An outer shell electron drops down to fill it, emitting characteristic radiation. Clinically, this total absorption creates the high-contrast blank spaces on a film. The energy is absorbed locally within the tissue. Now look at the competitor on the right. Compton scatter targets the atom's perimeter, striking a loosely bound outer shell electron. The photon only transfers a portion of its energy, ejecting the electron, while the surviving photon deflects in a new direction. The exact amount of energy the photon loses depends on the resulting angle of that deflection, making it an incoherent process. While photoelectric absorption creates clean boundaries, Compton scatter throws deflected photons toward the image receptor, resulting in diagnostic noise. What physical properties of the patient determine which of these two interactions occurs? This formula for the Compton attenuation coefficient calculates attenuation based on the material's density divided by photon energy. Scatter scales directly with mass and electron density and decreases slightly as energy increases. Notice it is independent of the material's atomic number, Z. Except for hydrogen, almost all materials have roughly the same number of available outer electrons per gram, removing the atomic number's impact on Compton scatter. The formula for the photoelectric linear attenuation coefficient, represented by tau, relies heavily on Z. Photoelectric probability scales with the cube of the atomic number and is inversely proportional to the cube of the photon energy. Because of that cubed relationship, high Z materials like bone or lead favor photoelectric absorption. This is why they appear stark white against low Z soft tissues. As photon energy increases, photoelectric absorption collapses at a rate of 1/e cubed. High-energy beams are ineffective at creating contrast in dense structures. This graph maps photon energy against attenuation. The downward slope follows the inverse cube rule until we reach a sudden spike known as the K-edge. When incident photon energy is slightly higher than the binding energy of inner K-shell electrons, a massive number of electrons suddenly become available for interaction. This energy match causes the probability of photoelectric absorption to increase sharply. Radiologists actively exploit this physical threshold by introducing high atomic number contrast agents, like liquid iodine, directly into the patient's body. Iodine, for example, has a highly specific K-edge of 33 keV. 33 keV sits perfectly within the diagnostic radiation range. Using iodine forces massive photoelectric attenuation, lighting up the vascular system with extremely high contrast. Let's scale back up to see how we measure a material's stopping power clinically. We use this formula to find the linear attenuation coefficient, or mu, representing the probability of a material attenuating the beam per unit of track length. The mass attenuation coefficient, or MAC, divides mu by density, removing physical density from the equation. By factoring out density, MAC reveals the inherent atomic stopping power of a substance, dependent only on its atomic number and the beam's energy. We also measure penetrating power using the half-value layer. This is the thickness of material required to cut a beam's energy in half. In practice, X-ray tubes produce heterogeneous beams, containing a wide spectrum of photon energies. Because low-energy photons are preferentially absorbed early in the tissue, they are filtered out as the beam travels deeper. As the low-energy photons are stripped away, the average energy of the surviving beam increases. We call this process beam hardening. This hardening results in a longer half-value layer as the beam moves progressively deeper through the patient. This graph visualizes the competition. The steep curve represents the photoelectric effect, and the flatter curve represents Compton scatter. At low X-ray photon energies, the photoelectric effect is the primary cause of attenuation. This produces distinct image contrast, but results in a higher patient radiation dose. As beam energy increases, photoelectric interactions plummet. At this intersection, Compton scatter becomes the dominant cause of attenuation. For low-density items like air, water, and soft tissue, the two processes reach equal probability at 30 keV. Bone maintains photoelectric dominance longer, crossing over at 50 keV. High-Z materials like iodine do not cross over until 300 keV, and lead remains in the photoelectric range up to 500 keV. Every clinical decision, from tube voltage to contrast selection, is a manipulation of these curves. The ultimate goal is to balance the hazy noise of Compton scatter against the pristine clarity of the photoelectric effect.